Hello, welcome back. We're going to continue, and today we're going to talk about the mathematics of uncertainty. Okay. Last class, I think we previously talked about went over the basics of taking derivatives. So make sure you know how to take derivatives of functions before taking this class. I'm Professor Wu. Let's get started. Basically, life is uncertain. There's a lot of uncertainty in life. Are you going to get a job after college? Or are you going to end up living with your parents? Or is it going to rain? Is your flight going to be delayed? There's a lot of uncertainty, right? Despite the fact that life is unpredictable, patterns often emerge. And for this is where the concept of probability comes in. It basically gives us a precise mathematical language to describe and quantify uncertainty, right? So this lecture we're going to kind of do a quick review of probability theories, right? Let's first understand how we symbolically represent probability. So far in this class lecture series, we talked mostly about linear algebra. And what I told you is that you want to picture lowercase x as kind of like a vector or some kind of variable, right? Either a single value or a vector of values. Whereas capital X, we're going to picture these more like a matrix or vectors of vectors. So that's linear algebra. In probability and statistics, the idea is different. We're going to represent X like more like one or multiple events that happened. The operant word is happened, past tense, something that happened. Whereas capital X is the random event that you don't know what happened yet. So it has many possible outcomes. So for example, let's say you have an election, right? With an election, well, you don't know what's going to happen. So this right here is a capital X. This is the event. And let's say there's candidate A, candidate B, right? So lowercase x is when candidate B won. All right, so this is X. What happened is equal to that B1. Whereas capital X is the event in general. So this is how you can kind of picture. And the way we write this is, let's say we will write that the probability that the event that happened is rain. And the probability of rain happening, we're going to say is 30%, for example, right? The probability that it's going to be sunny for the weather, 20%. Probability that what happened is going to be cloudy is 50%. So all three combinations will be the event, right? So capital X, it hasn't happened yet. And then if it did happen, well, if if it were to happen, you would say that if it were to happen, then the probability is 30%. We also represent sometimes with bar charts, right? You can look at it through like a table format, or you can look at a bar chart that tells you the probability and likelihood of each event. Now, when two events cannot happen at the same time, we call them mutually exclusive. So this allows us to talk about or the concept of or. The probability of A or B, it's simply the probability of A plus probability of B. So you have A, B, right? So you just add the probability together, then that's it. That is the probability of A or B. And then if you have probability A or B or C, right? That means you add all of them together, which when you add all of them together, you should get 100% or 1, right? All right, so over here, we have been talking about what we call the discrete distribution. So the things that could happen are clearly separated: rain, sunny, cloudy, right? There's no rain 0.5, like halfway to sunny. In this particular case, it's just rain, sunny, cloud. However, in other situations, like time, for example, so over here is another distribution. So over here, what happened is there are infinite number of times. So this right here is the probability distribution of the amount of time a student spent studying. right? So most of the student end up spending somewhere between 1 hour to 2 hour, right? So you can kind of picture we also have a bar chart, except you have a bar at every single infinitesimally small bar. You can kind of picture it that way. So they're infinite bars. And in this case, since they're infinite bars, instead of just looking at a single bar, which turns out to be probability of zero, what we tend to do is we look at an interval. What is the probability that somebody will study between hour and an hour and a half daily on this particular topic, for example? And when you are looking at this interval, then you are essentially summing every single possible bar that could happen in here, right? When you sum up all the bars, this turns out to be the area. So in order for us to find the probability for continuous probability distributions, if you're trying to find a continuous, so instead of summing them one at a time, we need to sum infinite of them. And when you sum up the infinite of them, it's equivalent to finding the area. So this idea of finding the area under some kind of function is really important in probability. Okay? So this is where the idea of integration comes in. So it turns out that integration allows us to take a function and then we can find the area between 2 points, A and B. So like this case would be 1 to 1.5, right? So you can find the area under the line, under the curve. And this is the idea of integration. And if you know how to do derivatives, like the 7 rules that we've covered so far, then integration is simply doing the derivative backwards. What do I mean by that? Well, remember in the previous lecture, we had a function. And if we take this function and we find the derivative, we got the derivative function, right? So this function tells us if as we increase the input at a certain point, is the function going to go up or down, right? This is what the derivative function tells us. Well, there's enough. We're going to look at the antiderivative. You can imagine that there's yet another function which we call the antiderivative. Well, if you take the derivative of this function, you're going to get the original function back. So therefore, doing derivative backwards, what I mean by that is that you are given this function and you're trying to find the function such that if you take the derivative, you will get itself back. Okay, so that's what I mean. So if you can remember how you take derivatives, right? If you know how to take derivatives, then you want to think derivative backwards to obtain the antiderivative. Okay, so that's the general idea. Okay, and the way we designate this is that the function that we want to find the area under, we put it right here. Right, so that's the function, and this is this function right here. Right, this right here, and we want to find the area between 2 points, A and B. Let's say from 0 to 2. So that we want to find that area between 0 and 2. So we want to find this area. That's what these symbols mean. And this is saying that x is the variable. Okay, so you can have multiple variables, but for this particular case, x is the variable. So you have a function where x is the variable, and you're trying to find the area between 0 and 2. So this right here is what it's saying, is asking you to do. And over here, this is 2, this is 4. So through geometry, we know that the area of a triangle is 4 times 2 divided by 2, 4. Okay, so we can find this through geometry, but now we're going to find it through integration. Okay, let's give this a try. Remember, I told you our goal, we start off with f of x, which is this right here, and we are trying to find a function, capital F of x, such that if we take the derivative of this, we're going to get f of x back. Okay? So another way to write this, if you take the derivative of the capital F, then you're going to get the original function back. And it turns out that if you try to do derivative backwards, the integral is simply x squared. Notice how if you take the derivative of this, you will get the function back, right? Because 2 comes down, right? So this function f is the capital F of x, x squared. Okay. Now, once you discover the antiderivative, you can now use this to find the area between 2 points. How do we do that? Well, to find the area between 2 points, let's say you want to find the area between point A and B, right? So like A and B. You simply plug B into the function and minus A, and this will give you the area. So in this particular case, I think we're trying to find this triangle here, which is 2, 4, right? So we're trying to go from 0 to 2. So what we do is we plug 2 into this and we plug 0. So it'll be f of 2 minus f of 0, which would be, so the function is x squared, so it's 2 squared minus 0 squared equals to 4. So the area is equal to 4, which corresponds to our previous answer through geometry, saying that it is 4. Okay, so integration basically just gives you a way of finding the probability by finding the area under a curve. Now, when you're out at work, you can also run integration if you download the scikit-learn, the scientific Python library, so SciPy. And all you have to do is, let's say you have a function. Remember our function is 2x, right? Right here, 2x. So this is our function. If we just define our function, we can then put this function f into what we call the quad function, and then the interval. So it's saying that this is the function that we want to find the area, and we want to find the area between 0 and 2. And then it outputs the area, which, as we already know, we've seen many times that it's 4. Okay, so this is how you can essentially find the area under the curve using Python. Here's another example. All right, what is the probability of just one single point? Like just one single point. Well, if you have one single point, that means you're going from 1 to 1, right? So that's the interval, A to B. And then you will be plugging f of B minus f of A, right? So if it's 1 to 1, then it'll be 1, 1 equals 0. So this tells you that for continuous distributions, the area of a single line is 0. And it makes sense because it has no width. Right? You have to have some kind of interval. Like A and B cannot equal to each other. If they are equal to each other, then they're just going to cancel each other out, right? So this is, this is going to give you a 0. Another example here is between 0 and 1. So what is the probability that x is between 0 and 1? That's what this is saying. What is the probability that x is between these two numbers? So between 0 and 1, then we want to find this, right? So this right here is the function we have is half x, right? So this is f of x. So what is the antiderivative? Yeah, what is the antiderivative? Well, you have x. So it has to be 1/2. Actually, what did I say? Yeah. So the antiderivative is 1/4 2. 1/4. And then 1/4 2. Yeah, right here. 1/4 2. Okay, so if this right here is when you do the derivative backwards, this is equal to f of x. Notice that if you take the derivative, you will move this down, right? So this will become 2/4 x2 minus 1, which is 1, which gives you 1/2 x. So you see, this right here is the antiderivative, because if you take the derivative, you get the function back. And now all we have to do is plug 1 and 0 in, like such. If we plug 1 and 0 in, right? So 1, if you plug 1, 0, giving us the area. Okay? So this is the general idea. All right. Now, you want to pause the video. Make sure you can do all the problems here. First, do it by hand. And then you want to use Python's automatic integration to confirm your results. Okay? All right, so here's the solution for the problems. So pause the video here, and then you can pause the video here again. I also include the code solution. All right, so let's move on. Now, previously what we learned is that this is telling us the probability of some event happening. Well, some event is just one thing. What if in real life we have multiple events happening simultaneously? So for example, we would have two events. So this is right here saying probability of x and y happen. This right here is probability of x and y and z happen. So and is the key. Okay, we're talking about when you see multiple variables simultaneously, it's always going to be an and. And we call these kind of distributions that has multiple variables joint distribution. Joint distribution. So you want to recognize these symbols. Now, with 2, 3, 4 variables, you can write it this way. However, if you end up having like hundreds of variables, then it gets complicated because you don't want to write 1, 2, 3 all the way to 100, right? So in probability, what we do is we just write p of x, and we assume that x is a vector of variables. So x could be x1, x2, x3, so on and so forth, right? So writing x, depending on the context, you can just assume that's going to be like multiple variables. All right, so the next one is called the OR logic. So we right here are the AND logic. The OR logic, well, when you want to find a probability of two events, A and B, right? We previously say that if there's no overlapping, then it's just probability A plus probability of B. However, if there are overlappings, like this, A, B, this area overlaps. So if you want to find the area of this, if you have A, B, then you are double counting the area in between. So you kind of need to remove probability of A and B, right? Because you're double counting here. So the OR logic, probability X OR, which we use the union symbol for OR, is probability like the first one, second one minus their joint distribution. And with joint distribution, especially two of them, we can visualize them as like a chart, right? So this right here, I ask you what is the probability of x equals to 0 and y equals to 0. So x equal to 0, so it's 0. Or probability x is equal to 1, y is equal to 1, then you'll be this one, right? So you can look at the chart and like very quickly figure out what the probability is. Now that we have the idea of joint distribution. If we have a joint distribution, does this include the original distribution? Can we get P of X and P of Y out of the joint distribution? And the answer is yes. And the process of doing this is called marginalization. When you're dealing with joint distributions like this, for example, right, you may need to be able to get just a part of the distribution, like one of the variable. And getting this is pretty easy. Let's say you want to find, this is right here, here's a table, and it's easy to visualize. If you want to find the probability x is equal to 0, well, then that's simply probability of x equals to 0 and probability of y equal to 0, this one, plus this one, plus this one. So you probability of x equal to 0 is basically the summation of all these. Probability of x equal to 0, y is equal to 1, and then plus probability of x equals to 0, y equal to 2. All right, y equals to 0, y equals to 1, y equals to 2. So the way we like to write them, probability of x is equal to 0, is the summation of probability of x equals to 0 and y equals to I. And we're summing them. So we're looping through each y value so we can kind of sum them together. Okay, so the idea is the same. What if you have probability x equal to 1? Then we're trying to sum up all the values where x equals to 1 for every possible I. For every possible I. So we'll be summing this one up. And this works either way. You can also do something like probability of y equals to 0, right? In that case, you need to sum it up horizontally. So probability of y equal to 0 is equal to summation of probability of x equals to I. So you're looping through x, y equals to 0, I. So you're kind of constantly, you're doing the I, x equals to 0, x equals to 1. Right? So you're summing this up. So if you want to find this one, you sum this one up. So this equation is basically describing what you are seeing visually, right? If you want to find the probability of this one, these are all the possibilities. So that right there is marginalization. Now, when you're doing this right here is an example of discrete, right? Discrete. But you can also do continuous. With continuous distribution, then you are also summing, except you have infinite sums. And to deal with infinite sums, which becomes area, then you need to once again perform integration. So remember, with x, you want to sum up all the y. With y, you want to sum up all the x. And the idea for integration is if you have p of x, then you need to sum up through integration all the y's. Conversely, p of y, then you want to sum up all the x's. Right? So the idea is exactly the same. Remember here, you're summing up all the x. Here, you're summing up all the y's. So integration allows you to do marginalization in when you have a joint distribution. All right, let's pause the video again. You want to quickly go over these questions. Pause the video, and make sure you solve this one. All right, this solving this will give you a lot of insight. Now, this right here, you're trying to find p of x, right? Therefore, you need to find the integral of y goes from 0 to infinity for this right here, theta 1, theta 2, e to the minus theta 1, x minus theta 2, y dy. Now remember, if you're trying to get p of x, then you need to sum up all the y's. Therefore, y is the only variable you need to worry about. All right, pause the video, give this a try. And over here is the solution for part 1. Here's the solution for part 2. Okay. All right, so now this leads us to the next concept, which is called conditional probability. Well, if I ask you two questions to demonstrate conditional probability, the first question is, what is the probability you're going to have a good date tonight? So you're going on a date, and what is the probability? And maybe the probability is of a good date is like 99%, right? Maybe that's great. However, however, notice how the probability of having good day changes depending on additional information that's given to you. So what is the probability of having a good day? What if you're given something else that you will be talking about your ex the whole time? So this idea of this example is to demonstrate that the probability of an event could change depending on additional information that's given, right? And this right here is where conditional probability comes in. What is the probability of some event conditioned on the additional information that is given? And the way we write conditional probability is like this. This is saying, what is the probability of X happening given? So this symbol is given that Y is known. That's what that's saying. Given Y happened. So what is, and this is the backwards, what is the probability of Y given that X happened? Okay. So this particular example, we would write something like, what is the probability of having a good date given that you're talking about your ex the entire time? All right. Now, the equation for conditional probability is calculated this way. So this right here is the equation. And if you just look at it, you can try to remember this equation, but I don't recommend trying to remember this equation. Instead, it's much easier to understand the concept of conditional probability. And if you understand the idea of conditional probability, then this equation just kind of emerges on its own. Like you can just calculate it on your own without memorizing the equation. I mean, on the exam, you're going to have like 30 equations. If you try to memorize all of them, it's not going to work out very well. Better if you understand the idea. So where did this equation come from? Let's look at this example here. This right here is two variables, right? Probability x, probability of y. Well, it has probability emerges out of this concept called a total space, possible space. Okay, so if what is the probability of x and y if nothing was given, right? If I didn't tell you any additional information, I just ask you what is the probability of x equals to 0, y equals to 0. So it's, let's say you want to find a probability of x equals to 1, y equal to 0. So it's this one here, right? So it's easy. It's just 0.2. You can visually see this. But what's actually happening is that if no additional information is given, the total possible space are 6 possible outcomes. 1, 2, 3, 4, 5, 6. So there's 6 possible outcomes that can happen. And the probability of the total possible space is equal to 1, right? Because, well, if you add all of them up, it is equal to 1. So what's happening is we are taking the probability that we're asking about, 0.2, and we're subconsciously dividing by the total space, which is equal to 1. And therefore, it doesn't matter. We can just keep this number. But keeping this idea of total possible space in mind really, really helps with conditional probability. That in reality, when we look at this, it's not this. It's this number divide out of the whole possible space. Okay, it's this number out of the entire space of things that could happen. Okay, well, what if you now are given some additional information? What is the probability of x equals to 1 given y is equal to 1? Well, that changes things slightly because we are told that y is equal to 1. If that's the case, then this is impossible. This is no longer a part of the total possible space. And this is also no longer a part of the total possible space. So what is the probability of x equals to 1 given the, which is 0.1, divided by the total possible space, which is 0.6? Okay, you see, you are taking this out of this, and that is therefore the probability. And what is this? This right here is simply probability of x equals to 1 and y equals to 1. And what is this here? Right? The summation of all probabilities. Well, that is just the probability of y equals to 1. And this right here is the probability of x equals to 1 given y is equal to 1. Notice how this right here is exactly the same as this equation. So you can try to memorize this equation, or you can simply remember the total possible space. Right? If you remember the total possible space, you just look at the total possible space, and it's asking you about this. You just take this divided by the total possible space. And this is a much easier way to remember than this equation. Although once you get used to this equation, then it gets easy. But like this is where this equation came about. All right, so now pause the video again and see if you can answer these next set of questions. You want to like really think through the idea of total possible space, and then really merge these ideas with this equation. Okay, pause the video. I'm going to move on to the solutions. Okay, these are the solutions. Pause the video. You can watch these. All right, so conditional probability help us define independence between two random variables. So remember, when we are doing linear algebra, we have the idea of independence, right? So independence in linear algebra and probability are different. So linear independence in linear algebra, it's saying that you don't have redundant vectors, right? So if you have this, right? Notice how this vector is redundant because you can use these two to reconstruct this vector. So the definition is very specific for linear algebra independence, and we check it by v plus alpha 2 v2 plus alpha 3 v3 equals to 0. So we use that null space idea, the idea of finding the null space, and if the null space is trivial, then it's like independent. So that's dependence in the idea of linear algebra that we've learned so far. But the idea of dependence and independence in probability is different. Okay? So we were learning this equation, right? So this is the definition of conditional probability that we just learned. And we basically can do a really quick maneuver and just move this here so that we get an expression for P of X, Y. So we have a joint distribution P of X, Y, which is equal to this. All I did was move that over here. So this right here is telling us that probability of X and Y happen is equal to the probability of X given Y times probability of Y. So that's what it's saying. Now, this relationship assumes that there's some dependence between X and Y, right? So when you have a good or bad date given, and let's say the Y is what you talk about. So talk about X the whole time. All right. So there's dependency. However, what if the question why is something else? What is the probability you have a good date given that it rained 4 years ago in Thailand? Okay. Well, do you think the probability you having a good date or not going to have any impact given that it rained 4 years ago on the same day in Thailand, right? So in this particular case, I mean, unless there's some crazy butterfly effect, chances are the fact that it rained in Thailand 4 years ago has zero impact on the probability you're having a good date. And in that case, it's saying that P of X given Y, right, doesn't matter. Therefore, P of X given Y is simply equal to P of X. No matter what you discover about Y, the probability of X does not change. Does not change. This right here is the core idea of dependence, right? If they're the same, then they're not dependent because whatever you discover about Y, it is not changing P of X. And therefore, the definition of independence is simply you get rid of this here in this relationship. This right here is the definition. Notice the difference between these two. So this is saying that there is dependence. This is saying that there's no dependence because given Y doesn't give you extra information. So the definition of independence is when the joint distribution is equal to the product of each, right? So also means X, Y, Z. If you have three of them, it will be probability of X, probability of Y, probability of Z. So this right here is saying that all the probabilities are just independent of each other. And this is how you can understand the idea of dependence. I'm going to skip IID. Okay, so conditional probability, what we just learned, leads us to a very important equation. Well, let's make some observations. We can do probability of X given Y. We can also do probability of Y given X. And from probability of X given Y, we can do a manipulation to get the join. And probability of Y given X, we can also do a manipulation. So this is observation A, observation B. And what I'm saying here is that we have the joint distribution is equal to this. But the joint distribution is also equal to this. Therefore, these two must equal to each other, right? Because they both equal to the same thing. And we can put them together. When we put them together, this is called the famous Bayes rule. Okay? Of course, most of the time with Bayes rule, we move this either over here or we move this over here. So Bayes rule, most of the time you see it this way. Okay? All right, so now we can hopefully you understand how the equation works, and you can use the practice using Bayes rule. All right, pause the video and see if you can solve this problem now. Okay. Here's the answer. And that's it for today. I will see you in the next lecture.